Hi, and welcome to Dr. V's AP Chemistry webcast. Today I'd like to talk about concentration units. Chemists use a variety of concentration units to discuss solute-solvent ratios, and they show up in lots of different contexts. And so it's really important that you know what the common units are. The most important unit is molarity. We'll also do some percent by mass problems. Along with that, we'll do parts per million and parts per billion, which are really more important in environmental studies than in AP Chem, but they all go together. And finally, the mole fraction may also show up here. We'll also solve some typical problems. You know that's my emphasis, so you can feel really confident if you ever encounter any of these. And if you're an AP Chemistry student, you certainly will. Let's start with molarity. Definitely the number one concentration unit for chemistry students. This is the go-to unit for chemists when they're talking about solute-solvent ratios. So the molarity is defined as the moles of the solute divided by the volume of the solution in liters. Things to watch out for. Molarity is always written with a capital M. A lowercase letter would actually indicate a different concentration unit. That's not part of AP Chem right now. So that's kind of an important little detail. And also when you're doing these problems, you want to make sure that you're talking about the total volume of the solution. It's not the volume of the solvent. Remember, they don't always behave additively, and so you do need to measure that total volume of the solution when you're done. The other thing you want to just keep in mind, and this is a more subtle point, is that volume can change with temperature. So technically, molarity is temperature dependent. We usually just report it at 25 degrees Celsius, but in principle, it could change. So let's do a sample problem. A very typical problem you might encounter. A solution is prepared by dissolving 35 grams of sodium chloride in water and bringing the mixture to a final volume of 675 milliliters. Calculate the molarity. Okay, well, I always like to start by thinking about the molarity formula. I need the moles of the solute, and I need the volume of the solution in liters. So to find moles, we're going to take the grams and divide by the molar mass. You've done this a lot, I'm sure. You do want to pay attention to your sig figs, so when I do that, I get 0.60 moles of sodium chloride. The solution volume has to be in liters. This is another place where it's really easy to make a mistake. So I have to convert my milliliters to liters. Remember, there's 1,000 milliliters in a liter. And I just substitute and evaluate. Now, because I only knew the mass of the sodium chloride to 2 sig figs, in the end, I really only know the molarity to 2 sig figs, so I get 0.89 molar. Notice the capital M there. All right, or you could say moles per liter. Of course, that's fine as well. Let's do another problem. What mass of silver nitrate is required to prepare 275 milliliters of a 0.20 molar solution? Now, if you want, go ahead and try this on your own, and then I can walk you through the answer, or you can just sit and watch me do it. That works too. So again, I always like to start with the formula, and I like to rearrange it. I'm solving for a mass, which we know is related to moles. So the moles of the solute, here the silver nitrate, would be the molarity of the solution times the volume. Remember, the volume has to be in liters. So 0.20 moles per liter times 0.275 liters, right, when I convert my milliliters to liters, I end up getting 0.055 moles of silver nitrate. And from my periodic table, I can calculate the molar mass of silver nitrate. It's just shy of 170 grams per mole. Of course, we do want to have plenty of precision there. And so then I can just use my gram to mole relationship to find the mass of the silver nitrate. So the moles times the grams per mole would leave me with grams. And so I end up getting 9.3 grams of silver nitrate. Again, I can only report my answer to 2 sig figs because the molarity of the solution that was given had 2 sig figs. All right, so these really are important. You want to make sure you can do your molarity problems, go back and forth. They could show up in stoichiometry problems. They're going to show up in equilibrium problems. You really need to make sure you can do molarity. It's super important. Percent solutions aren't emphasized as heavily these days, but they're worth knowing about, and they're really easy to do. It's mass of what you want over the total mass of the solution. You have to make sure it's the total mass and then times 100. We do percents all the time, so this is something that should be quite comfortable for most students. This would be a mass to mass percent. There are other types of percent solutions. You could do mass to volume, volume to volume. You're supposed to specify what it is. Generally, unless you're told otherwise, it's okay to assume it's mass to mass. The other reason I mentioned percent solutions is that they're used a lot in medical applications for preparing IV bags and different treatments because they're easy to prepare accurately. So they do actually have a lot of everyday uses. So let's do a sample problem that's a percent solution problem. A solution is prepared by dissolving 1.45 grams of magnesium chloride in 750 grams of water. Calculate the percent of magnesium chloride in the solution, and we're told it's a mass-to-mass solution. All right, so if you want, go ahead and try it on your own, and then I'll walk you through. All right, so thinking about just the problem, a percent solution is the mass of what I want over the total mass. So it's the mass of the magnesium chloride over the total mass of the mixture. So that's something that students often forget to do the total mass. So it would be 1.45 grams, that's my solute, over the total mass of the mixture, where I have to add the 75 plus the 1.45 grams and multiply that by 100, right? Remember, total mass of the solution with these percent solution problems, and I get 1.90% mass to mass. I knew everything to at least 3 sig figs, so I'm reporting my answer that way. All right, let's do another percent solution problem. How many grams of potassium carbonate would you need if you wanted to prepare 1,400 grams of an 8% solution? Okay, so again, going back to our formula, what we're solving for here is the mass of the solute, which I called A for lack of a better term. The total mass is 1,400 grams that was given, and I have an 8% solution. I always recommend rearranging first before substituting. I know some of you don't like to do that, but it's really in your best interest, folks. So the mass of the potassium carbonate would be the percent of the potassium carbonate divided by 100 times the total mass of the solution. So I substitute and evaluate. So it was 8% of 1,400 would be 110 grams. Again, I only know things to 2 sig figs, so that's how I reported it. All right, so parts per million is really an extension of a percent solution. This is used a lot in water treatment, environmental situations. You can think of it as milligrams per kilogram of solution or milligrams per liter of solution, or like the more textbook definition for parts per million, which is often written ppm, the mass of what you want over the total mass times 10 to the 6. Do pay attention to your units when you're doing these problems because they can be presented in several different ways. Parts per billion is a very similar kind of approach. It could be 1 gram per billion grams or a microgram per liter, or the mass of what you want over the total mass times 10 to the 9th. Again, just pay attention to your units to make sure that you're doing them correctly. I don't anticipate you'd see this on the AP exam, but you will see it in everyday life. So, for example, a 475 gram sample of drinking water is found to contain 0.12 milligrams of lead. What's the concentration in parts per billion? Okay, so we can think of that as micrograms per kilogram if we just think about our units. So do pay attention to that. So 0.12 milligrams of lead would be 120 micrograms. 475 grams of water would be 0.475 kilograms. I can substitute that in, and I get 250 parts per billion. Now, this is a problem I just made up because I felt like it. But of course, lead contamination is a huge problem. This would be 17 times the allowed limit from the EPA. So hopefully no one is experiencing anything that high. The other concentration unit that I wanted to discuss was the mole fraction. And this does show up occasionally, sometimes in your gases unit. Can show up in a few other places. So the mole fraction, which is sometimes given the Greek letter chi, or just an X, is the moles of what you want over the total moles. So you do have to have everything on a mole basis. The other thing to do is to pay attention to whether you're solving for the mole fraction of the solute or the solvent. This can come up with things like Raoult's law when you're doing gas behaviors. Although that's not part of the AP curriculum, some of you watching this might encounter that in your class and need to know about that. So a typical problem for the mole fraction. 13.5 grams of nitrogen gas are mixed with 27.8 grams of oxygen gas. Calculate the mole fraction of nitrogen in the mixture. Now, what you really have to remember with mole fraction problems is that everything has to be on a mole basis. These are not gram based problems. That would be your percent solution. These are mole fractions. So it's moles of what you want over total moles. So we have to find the moles of nitrogen, the moles of oxygen, get the total moles, and then we can do our math. So to convert to moles of nitrogen, we're going to divide the mass of the nitrogen by its molar mass, which is 28. So we get 0.482 moles of nitrogen. Similar math for the moles of oxygen. I have to take the mass of the oxygen divided by its molar mass. Remember, both gases are diatomics. And I get 0.869 moles of oxygen. For total moles, I'm going to add those up. I had 1.351 moles. So now I can say, all right, I want the moles of nitrogen. So I'll do the moles of nitrogen over the total moles and report that. Now, one of the funny quirks of mole fraction problems is that it's always presented as a decimal. And you're supposed to pay attention to sig figs with this as well. So do just keep that in mind, that even though they're called mole fractions, it's always in a decimal format. All right, that ends this webcast. I hope you feel a little more comfortable with working with concentration units, especially molarity. That's your number one unit. And practice, practice, practice. That's really the key, folks.